In movies and on TV, advertising executives are often portrayed as suggesting that they run something up the flagpole and see if anybody salutes. Well, that's what we're going to do, because we're sure that you'll want to salute that enthalpic, that anti-entropic, that thaumaturgical thermodynamicist, the big calorie kahuna, the Houdini of heat, the potentate of potential, yes, king of kinetics, the ascendant emperor of energy, the one, the only, Professor Clint Sprott.
Welcome to the Wonders of Physics. Now, you probably wonder what I'm doing hanging around in a place like this. But I wanted to talk to you today about the physics of energy. And I wanted to illustrate a kind of energy that we call gravitational potential energy. And I have a lot of that kind of energy right now, and I'm going to convert it into light and sound by way of a generator over here. Okay, Kevin, let me go. So as I say, the physics of energy. Now, there are many things to understand about energy. One thing is that energy can never be created or destroyed. The amount of energy in the universe will always be the same. All we can do is convert it from one form to another. And I'm going to show you many examples of converting energy from one form to another today. Now, whenever we talk about something like energy in science, it's useful to have a way to measure it. And the way we measure energy is in something that we call a joule. And I've written the word over there. The word comes from the name of a man, James Prescott Joule, the son of an English brewer who lived about 150 years ago and did some of the most accurate measurements of the transformation of energy that have ever been done in his own private laboratory. And so we honor him today by measuring energy in units of joules. When I was up there on the scaffold, I had about 3,000 joules of energy. And I converted all of that energy into motion and eventually into electricity and heat and sound and light. And these are all of the areas of classical physics, because every area of classical physics involves a form of energy. Now I want to illustrate another example of converting energy from one form to another. And for this, I need a volunteer. Who will help? Come down here. Turn around. Tell us your name.
Paige.
Paige? Okay, Paige, you look pretty smart. You take science in school?
Yeah.
Is it a good subject for you?
Kind of.
Kind of? Uh-huh. What do you want to be when you get a little older, Paige?
Teacher.
A teacher? Yeah. Are you going to teach science, I hope? No. I guess we have a little work to do on you here, Paige. Well, anyway, we hope you enjoy the science that you're going to learn today, and maybe when you teach, maybe you can work some of this into your teaching. Paige, what we'd like you to do is turn to your right and walk over to my assistant, Mr. Lovell. Because we're going to have Paige illustrate the conversion of potential energy into kinetic energy using a 16-pound bowling ball suspended from a string or a wire from the ceiling in what we call a pendulum. A pendulum is any mass on the end of a wire or a string that can swing back and forth. Now, Paige, what we'd like you to do is to put your head against the wall and hold that right against your forehead. We'll help you a little bit. Oh, I guess you can do it. And when I say I want you to let go, are you ready? Mm-hmm. Let go. Put your hands down by your side and don't move. Once more. Thank you, Paige. Now, in this example, the pendulum started with about 70 joules of potential energy because it was up higher than it normally would be. And as the pendulum swung, that potential energy was changed into kinetic energy. Kinetic energy is the energy of motion. When I walk, I have kinetic energy because I'm moving. Now, over here we have another example of a pendulum. And this has a little smaller ball, but it's on the end of a string, and it can move back and forth. In fact, it's a little more complicated because this pendulum has a bunch of pegs. But if I bring the pendulum up, even with this yellow line, and let it go, it will swing back and forth in a somewhat complicated fashion, but it will never come any higher than that yellow line because that's how much initial potential energy it had. And so as it swings, it can never gain more energy than it started with. Now, as you watch that, you will notice that as time goes on, it swings less and less, and eventually it will stop swinging. So you may wonder, where did the energy go? Energy cannot disappear. The energy, in fact, is converted into another form of energy that we call heat. And heat is an important example of energy that we'll talk more about in a little while. So let me show you another curious kind of pendulum. Here we have a pendulum that will swing back and forth, and right next to it is another pendulum that will also swing back and forth. But these pendulums are connected together toward the top with a rubber band. And if I start with one pendulum at rest and the other pendulum swinging, the energy of this pendulum will slowly be transferred to the other pendulum through that rubber band. And so, as time goes on, this pendulum will stop swinging and that pendulum will begin swinging. And after a little while, this comes almost completely to rest. Now, as time goes on, you will notice that this one begins to slow down again, and this one speeds up. And in fact, the energy will continue to go back and forth, first in one pendulum, then in another. So you're not only seeing energy change from potential to kinetic, but you're seeing it change from one pendulum to the other and back again. Now, another example of that is this little gadget right here. This is a peculiar kind of a pendulum that swings back and forth, but it also has a spring on it, and so it can go up and down. And if I stretch the spring and release it, it will oscillate up and down. But if you watch carefully, you notice after a while it's not going up and down so much, but it's twisting. And then as you continue to watch, eventually the twisting ceases, and it's going up and down again. So the energy is moving back and forth from up and down motion to twisting motion, and then back again. And it will continue doing that. And this pendulum is called a Wilberforce pendulum, named after Lionel Wilberforce, a lecturer who lived in England about 100 years ago. And he gave many lectures like this. And he built this just to demonstrate this principle of the conservation of energy. So I'll put that up here so you can watch it a little more, and I'll start it going again just so you can watch it. Now, underneath this is another gadget that many of you have probably seen. There are 5 stainless steel balls hanging from strings. And I can give one of these balls energy, potential energy, by simply raising it up above its equilibrium position down here. Then when I release it, that potential energy is converted into kinetic energy, the energy of motion. And you know what will happen. When it hits the balls, a ball on the other end goes shooting out. And the fact that one ball comes in and one ball goes out is an example of the conservation of energy. The energy of the ball going in has to be transferred to the energy of the ball coming out. Now, what if we start with 2 balls like this? What will happen? That's right. 2 balls go in, 2 balls go out. And that's necessary in order for energy to be conserved. Now, a little bit more complicated. What if I do it with 3 balls? 3 balls in, 3 balls out. So energy is conserved in this demonstration, except that you know the balls eventually will stop swinging, and that's because some of the energy of motion is being transformed into other forms. Because of the friction of the balls swinging through the air, some of the energy of motion is transferred to heat. The air actually gets a little bit hotter as the pendulum stops swinging. Not only is heat being generated, but another form of energy. What is it? Sound, exactly so. Every time the balls collide, you hear the click. The click is sound energy, and that energy came from somewhere, and the only place it could have come from is from the swinging motion of the balls themselves. So these are interesting examples of the conservation of energy. Let me show you another example using this little can. an ordinary sort of can that once had something in it that one would eat. And I'm just going to roll the can along the table here for you. The table must not be level. Let me try it from this direction. Well, what's going on? We started out giving the can some kinetic energy, energy of motion. It was rolling. But eventually it came to rest. All of that energy disappeared. And then it turned around and it came back. The energy sort of magically reappeared. But remember, energy can never be created or destroyed. So that energy must have been stored somewhere. And I'll bet you can guess that somehow the energy was stored inside the can. And indeed, since this is science, not magic, I want to show you that inside the can is a rubber band, and the rubber band has some lead weights on it. And so, as the can rolls, the rubber band twists up, and energy is stored in that stretched rubber band. That's another form of potential energy. So the kinetic energy of rolling changed into potential energy, and then that potential energy came back in kinetic energy, and the can came back to me. So it's a very nice demonstration of the idea that energy is always conserved. It only changes from one form to another. Now, this is an interesting example because the can was moving in the same way that something would move if I were to walk, but at the same time it was turning. And in fact, there are two different kinds of kinetic energy. There's what we call translational kinetic energy. That's just when something is moving in a straight line. And then there is also rotational kinetic energy when something is turning like this, even if it's not moving anywhere. And the can was doing a little of each. And to illustrate that, I have another apparatus over here that consists of an axle, and around the axle is a rope. And the rope is connected to a 50-pound weight, or as we prefer to say, it's about 20 kilograms of mass. And that has a fair amount of potential energy, about 100 joules of potential energy, just by virtue of where it is. And I can take that potential energy and convert it into rotational kinetic energy of this object by simply releasing this mechanism. And you see, the potential energy of the mass was converted into rotational kinetic energy of the arm, which is going around. You also notice that the arm continues going around even after the weight has fallen off. And that may seem curious to you, because you may have always thought that to keep something turning, you need to connect it to some kind of motor or something. But in fact, if we could remove all of the friction, this would turn forever, because energy is conserved. The energy in the turning would remain there forever. And in fact, there's at least one good example of that. You know, the Earth rotates on its axis. There's no motor making it turn. It was turning millions of years ago, and it just continues to turn. Because there's little or no friction, energy is conserved, and so that rotational kinetic energy remains in the Earth for a long, long time. And so, these are examples of conservation of energy. Now let me show you something else that rolls. This is a very interesting demonstration, and it involves two balls, two stainless steel balls that are identical, except for the obvious fact that one is big and one is small. But they're solid, and they're made out of stainless steel, and one has a small radius, one has a large radius. Now what I'd like to do is to put these at the top of this plane and release them. And they're going to roll down the plane. Now here's a chance to test your physical intuition. Who thinks that this one will get to the bottom first? Who thinks this will get to the bottom first? Most people think the small one will go faster. Well, that's a pretty good bet because small animals run fast and so forth. But you know, in science, we don't just guess at the answer, and also we don't take votes. That's for politics. What we have to do is to go into the laboratory and do an experiment. And then however it comes out, that's the way it works. And so I'm going to release them both from rest, and we'll see which gets to the bottom first. Well, they more or less go together. There was very little difference between the rate at which they go down. And in fact, that's a general principle, that any two balls, no matter how large, how heavy, how big, will roll down at the same rate, side by side, so long as they're solid and uniform throughout. If they're hollow on the inside, then it's a little bit different. Well, let me show you an example of a similar thing that may not be quite so obvious. Here I have two discs. They're like wheels, and they weigh the same amount. They're made out of wood, and they both weigh the same, and they're the same size. Except you see there is an important difference between the two, because one of them has an extra weight on the center here, a little brass cylinder. The other has an equal amount of brass on the rim. And so although they weigh the same, the position, the location of the mass is different in the two cases. Now you can guess what I'm about to do. I'm going to roll these two down the plane. Who thinks this one will get down first? Good. Who thinks this one will get down first? About half and half. And that's fine. In science, we call these theories, and it's perfectly okay to have a theory. But we have to test it. So let's see. So you see, this one got down significantly before the other. Now, you know, you all have energy coming into your homes. This energy comes in at least two forms. One form is in electricity. You buy electricity from the power company, and they sell you electric power according to the number of kilowatt hours. Well, a kilowatt hour is another way to measure energy, like the joule. In fact, a kilowatt hour is almost 4 million joules. It's a lot of energy. And the power company sells you electric energy for about 2 cents for every million joules. So it's a lot of energy, and it doesn't cost very much. Now, a kilowatt hour, of course, is the amount of power that you consume if you ran a 1,000-watt light bulb for 1 hour, or a 100-watt light bulb for 10 hours. And so if we ran that for 10 hours, it would use up 1 kilowatt hour. And so this idea of power is closely related to energy. Power is the rate at which energy is transformed from one form to another. So when we say that light bulb is 100 watts, we're saying that in every second, 100 joules of electricity is converted into light and also into heat, because you know light bulbs put out heat as well as light. In fact, light bulbs put out more of their energy in heat than they do in light. And that's one reason there's a lot of interest in making more efficient light bulbs that make more light for a given amount of electricity. So that's the concept of electric power.
Yeah! 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 Yeah!
What is this?
It is I, the Blue Power Ranger. Yeah! I heard that you were doing battle with the evil Physignoramus, the evil specter of science illiteracy, and I thought you could use some help. Yeah!
Indeed, we're talking about the conversion of energy from one form to another.
Excellent. This is something I know a lot about, being a Power Ranger. Do you have any way for me to turn energy from one form to another?
I know. We could have you turn your muscle energy into electricity.
That sounds like a perfect job for me. How can I do it?
On our exercise bike, right over there.
Ah! Oh! Yeah! Yeah! Yeah!
No, that's not how you ride it. No, no.
I wasn't trying to ride it. I was afraid that this was bicyclotron, the evil bicycloidal morph. But I will now turn my considerable Power Ranger power into electrical power. Yeah! 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 Oh!
Very impressive.
Professor Sprott, I was working very hard. I must have been putting out at least 10 horsepower, I think.
Oh, no, not at all. A horsepower is about 750 watts, and at best you were doing maybe 100 watts.
Oh, maybe I'm not as powerful as I thought after all. But how about some more demonstrations on energy conversion?
Well, how about if we convert the energy of motion into heat?
Yes! Yeah! I know just what to do, but I will need your help. I want you to take your hands and clap them together. Yeah! Now I want you to rub them. Faster, faster. Yeah! Yeah! Faster. Now take them and touch them to your cheeks. Yeah! Ah, what do you feel? Heat. Yes, we took the mechanical energy of our hands rubbing, and through the force of friction, we turned it into heat energy, which we could feel on our cheeks. Do you have any other ways we could do this, Professor Sprott?
Actually, we do. Right over here, we have an apparatus.
Ah! Yeah! I see just how this will work. I have here a drill press. Yeah! And inside the drill press is a wooden dowel. So I will turn on the drill press. Yeah! And I will press the wooden dowel into the block of wood below it. Yeah! 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 Oh! What do you see? Smoke, yes! Yeah! Woo! Yeah! So what we did is, again, turned mechanical energy through the force of friction into heat energy. And we created so much heat energy that it started the wood smoking. Yeah! You know, Professor Sprott, if you were trapped in the woods with no way to make a fire, if you had a drill press with you, that'd be the perfect way to do it.
Or a match.
You physicists always try to make things too easy.
Right.
Well, do you have any other demonstrations I can do? Maybe something more with a bang.
With a bang. Ah, I know. We have over here a little bottle that has a little bit of ethyl alcohol in it.
Ethyl alcohol. You know, Professor Sprott, this reminds me of something. Do you know what that reminds me of?
A bottle of ethyl alcohol.
I think I should be the one giving these demonstrations. No, it reminds me of a car engine. See? This bottle is like the cylinder of your car engine. Inside is ethyl alcohol. That's like the gasoline or fuel. For anything to burn, it needs some oxygen. Yeah, yeah, yeah. All right. Then to complete the engine, we need a piston. That's what this cork is for. Yeah, 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 yeah. Now, you may notice that in the sides of my cylinder, there are two screws. They come through and almost touch at the middle. All they need is a spark from a spark plug.
Spark. We have just the gadget, a little Tesla coil.
Yeah, this will do perfectly. Let me turn it on. Oh! It sounds like a drill, doesn't it? But it's not. It creates a giant spark. Yeah! Well, let's put this spark to our spark plug and see what happens to our little model car engine. Yeah!
Well, you know, that's really impressive. But let me show you another way to make an explosion.
Ah!
This uses a special liquid that I have here called liquid nitrogen. That's right. Liquid nitrogen looks a little like water. You pour it out, except it doesn't make things wet. And that's because this is very, very cold. It's at a temperature that's about 321 degrees below zero. You know what that is in Celsius?
Oh, I have no idea.
Maybe I should give this lecture. That's about 196 degrees below zero Celsius, or a mere 77 degrees above the absolute coldest that anything can be. And one thing we can do with this liquid nitrogen is to take a small stainless steel cup and lower it down into the liquid. You notice the liquid nitrogen boils very vigorously. And it does so because the cup is much warmer than the liquid nitrogen. And so it causes it to boil. But as time goes on, the cup eventually cools down to the very low temperature of the liquid. And when that happens, as it has now, the boiling stops, and I can remove the cup and show you that it has in it a little bit of liquid nitrogen. If I shake it, it spills. I don't want to spill too much because I want to take this cup and lower it down into this brass cylinder. And then take a cork and hammer it on.
Yeah, 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 yeah! Whoa! Well, I've got to get out of here. See you all later. Yeah!
Well, we just never know who'll drop in, do we? But I'd like to continue talking about energy. And remember I said that there was a form of energy that comes into your homes, electric energy? But there's another form that comes into most of your homes, and that's in the form of natural gas. And we have some natural gas back here, and I'm going to turn it on, and it will come out a gadget here that we call a Bunsen burner, and I'm going to take a match and convert some mechanical energy into heat energy by striking the match, and then I'll light the burner. Now you notice the burner is just underneath a beaker of water. It's about a pint of water, or as we prefer to say in science, it's about 500 milliliters of water. And you all know from having done this on your stove at home that if I wait a while, that water will begin to boil. And eventually it will all boil away. And in fact, the amount of energy required to boil 1 pint of water is just about exactly 1,000,000 joules. 1,000,000 joules of energy required to boil 1 pint of water. Where does that energy come from? It comes from the natural gas. Natural gas has a form of potential energy. It's in the molecules that make up the gas itself. They're held together like masses on springs. And that energy is very large. And you know, when we buy a natural gas, we pay only about 1/2 cent for 1,000,000 joules of gas energy. And that's to be compared to electric energy, where we pay about 2 cents for every 1,000,000 joules. So you see, if you were going to heat your house, it costs about 4 times less to heat it with natural gas than it does to heat it with electricity. And so there are various forms of energy, and they all have their purpose. Now, the next thing I want to show you involves another example of transforming electrical energy into heat energy. Over here I have a little heating coil that's connected to a plug that goes in the wall back here, and I've turned it on, and an electric current will pass through that coil. The coil will get hot. The electric energy will be transferred to heat energy. Whenever something is hot, it radiates. It radiates what we call infrared radiation. It's like light. It's a form of radiation, and we can even focus it with a mirror. And here we have a parabolic mirror, and the source of heat is right at the focus of that parabolic mirror. Now, if you notice, way down on the other end of the bench over here is another parabolic mirror. And right at the focal point of this parabolic mirror is something. Can you tell what it is? That's right. It's a match. And we're attempting to focus all of that electromagnetic wave energy, that infrared energy, on the head of that match. And if we're very lucky, as time goes on, it will get hot enough that just maybe it will burst into flames. So I want you to watch that while I go on and talk about something else. And if it should catch on fire, I want you to holler out so that I don't miss it, because I want to be sure to see that if it happens. Now, I have here another gadget that we call a radiometer. A radiometer has some little plates in here that are silver on one side and black on the other side. And you notice they're spinning around. And that's because light is hitting those, and the light energy is being converted into rotational kinetic energy. And to show it to you a little bit better, I can shine a bright light on it like this, and you see it goes around quite rapidly. Oh! So we converted the energy of the light into rotational kinetic energy. And you know, a lot of people misunderstand this little gadget that we call a radiometer. A lot of people think that the silver side, of course, the light hits and it bounces off, and you might think, therefore, that the light would push harder on the side that's silver, whereas the black absorbs the light and it doesn't come back off. And you might think the light would push not quite so hard on the black. That's a good theory. Unfortunately, when you shine the light on it, it goes around in the opposite direction. So it's a good theory, but it's wrong. What actually happens is that the light strikes both sides, and the black, absorbing more light, gets hot. When it gets hot, the molecules in the material start to move very fast, and so when an air molecule hits them, the air molecule bounces off with a lot more energy and transfers a lot of that energy to the thing that's moving and pushes it around. So the black side is the one that is pushing in the forward direction. And so it's an interesting example of the conversion of one form of energy into another. Now, we Another example of energy is sound energy. And of course, I'm making that kind of energy when I'm talking to you. The vocal cords in my throat are vibrating very rapidly, and that motion is being converted into a kind of a motion of the air, a wave-like motion that we call sound. Now, in order to make a sound, we need to make something vibrate very rapidly. And here's an example of something that will make a sound. Do you know what this is? That's right, it's a tuning fork. It's a little U-shaped piece of metal. You strike it with a mallet, and it vibrates very rapidly and makes a sound. So let's try that. Now, you probably couldn't see it vibrating because it was going back and forth about 400 times every second. And that's too fast for your eye to follow. But we have here another tuning fork that's quite a bit bigger. And so it will vibrate at a slow enough rate that you will actually be able to see it vibrating with your eye. The only problem is when it vibrates too slowly, although you can see it, you can't hear it. Because you can only hear things when they vibrate at least about 20 cycles every second. And this will vibrate only about 10 times every second. So I'll just start it vibrating. And you can see that vibration. In fact, there's a better way to exhibit this. We can use what's called a strobe light. A strobe light is a very bright light that flashes very often. So here we have our strobe light that's flashing. And I'll hit this once again to get it vibrating. And we'll put it in the strobe light. And you'll be able to see how it looks like this almost comes to rest. And we can make it go very slow. But of course, all we're really doing is catching it at various parts of its vibration. And so it looks like it's moving very slowly. And so this is an important way that scientists have for observing things that are occurring very rapidly. It's a way of slowing things down so you can observe them more easily. Now here's another example of converting motion into sound. This, believe it or not, is a musical instrument. You know what it's called? Not a tuning fork. It's called a carugaphone. And when you spin it around, and if I were a better musician, I could play a tune. But you get the idea. We are converting the rotational kinetic energy into sound energy. And so there are many examples of this. And every way we have of making sound involves converting motion into a sound wave. Here's an example of a way of making sound that every one of you has at home. If you have a stereo set, or a radio, or a television, or even a computer, it will have one of these in it. Do you know what this is? That's right, it's a speaker. Sometimes we call it a loudspeaker because they can be very loud. Now, a speaker is a very interesting example of changing energy from one form to another. Did you ever notice that there are two wires that come into a speaker? They bring in the electrical energy. That electrical energy goes through a coil of wire in the speaker and is converted into magnetic energy. The magnetic energy then pushes the cone of the speaker up and down, and it converts it into kinetic energy of motion. That kinetic energy then makes the air vibrate and makes a sound wave. The sound goes to your ear, where it's changed back into the kinetic energy of your eardrum, which vibrates back and forth. So this speaker we have connected back here to an audio oscillator that makes the speaker vibrate. And so if I turn it on, you can hear it. And as I go up to a higher frequency, it's vibrating more and more rapidly. I can also go down the other direction to a lower frequency, and it will vibrate less and less rapidly. So you can see the little ping pong ball. The little ping pong ball was bouncing up and down because the speaker was bouncing up and down. Now, you probably all know that a speaker is good for changing electrical energy into sound. But you may not know that a speaker will also work the other way. You can use a speaker to convert sound into electricity. Same speaker. So we have the speaker, and it's connected back here to the input to our public address system that comes out over here. And when I turn this up, if I touch it or tap it, you can hear that I'm converting the motion of the speaker going up and down into electricity and eventually then back into sound, and that's what you hear. And in fact, I don't have to touch it. Even just talking at it, the air itself will vibrate the speaker. And if I get close and turn it up, you'll be able to hear me talking through the speaker. And if I get it up too high, we actually get feedback where the sound from those speakers goes into that speaker, and it goes round and round, and it gets louder and louder. Why, it's Krista and the semitones.
How are you doing?
Oh, I'm doing just great. What are you folks doing here?
Well, we've written some words to go along with your Wonders of Physics theme song that explain how we first got interested in physics. We'd really like to sing it for you.
Oh, that's wonderful, and I would love to hear that, but you know, you came at kind of a bad time. I'm right in the middle of giving a lecture here.
Oh, I'm sorry. Hey, would you guys like to hear the song as well? We do?
Yeah, that'd be great.
They're going to let us sing it. Come on.
Wonder, do you wonder?
Listen, oh, do you ever wonder? Wonder why oil and water don't mix? Wonder why sunshine makes a rainbow? It's the wonder that makes people study physics. Stars way up in the Milky Way, quarks smaller than anything, have the same physics that they all must to be, and that just makes me want to sing. Listen, oh, do you ever wonder? Wonder why iron likes a magnet? Wonder about how your TV works? It's the wonder that makes people study physics. Wonder.
Krista Mollman, accompanied by Paul Fontana and Renee Nesendal.
Thanks, Professor Sprott.
These are some of the graduate students who actually take a version of this show into the schools around in the local area. And maybe some of you have seen them give the show. We also have a little bit of a special treat today because the person who wrote our theme music is in the audience. Professor Jim Latimer, would you stand up? Well, there's just no end of surprises when you attend a Wonders of Physics lecture. But I do want to move on and talk a little bit about the physics of electricity, because electricity is a very important example of energy. And here I have a gadget that makes electrical energy. And it makes it by my turning this crank. And when I turn the crank, you can see a plastic disc here that moves around. And when the disc moves around, it stores electrical charge in these jars. And that electrical energy eventually will build up to a very large voltage. And the voltage is a way we have of measuring the amount of energy that something has. And you see, when the voltage gets high enough, about 30,000 volts or so, eventually a spark occurs between those two balls. And as long as I keep turning, I can continue converting my mechanical energy, energy of motion, into the electrical energy of that spark. And that spark, by the way, is something that we call a plasma. And a plasma is another important form in which energy can appear. Now, there are other examples that I can show you of electrical energy. I want to now show you perhaps the most dramatic demonstration you'll see today, and it involves a 1,000,000-volt Tesla coil. And for this, I need a volunteer. Who would like to help? Come down here. Turn around. Tell us your name. I'm sorry?
Brandon.
Oh, Brandon. Brandon, are you good at science? Kind of? You want to be a scientist when you get older, I suppose, don't you? What do you want to do? You want to be famous? Well, there are lots of famous scientists.
Yeah,
Well,
a dancer.
a dancer. Oh, you know, I dance. I love dancing. That's a lot of fun. But you know, you need physics when you're dancing because there's motion. There's all kinds of energy involved. Well, we'll talk about that later, Brandon. Brandon, what I'd like you to do is turn to your right and walk over this way. Turn to your right again and step right in and have a seat in what looks very much like an electric chair. Now, over to Brandon's right is a 1,000,000-volt Tesla coil. Now, Brandon, as long as you don't stick your fingers through the cage, you shouldn't feel a thing. Don't let the noise bother you. Thank you, Brandon. But I want to now show you another example of converting electrical energy into some other form. Back here I have what we call a capacitor. It's a device that stores electrical energy. And this capacitor will store about 3,000 joules of electrical energy. And when I've stored the energy, I'm going to discharge the capacitor into a little strip of aluminum foil, the same aluminum foil you may have in your kitchen at home. And we'll see what happens. Before I do that, though, I'm going to put on my goggles for safety purposes. You'll be safe because of this little piece of plastic right there. So I'm going to begin charging the capacitor, and you will see it's charging up by looking at this meter. The meter is now coming up to about 3,000 volts. When it gets up to about 6,000 volts, I'm going to discharge the capacitor into this strip of aluminum foil. Now, you may notice Mr. Lovell with his fingers in his ears. If loud noises bother you, you may want to cover your ears. Is everyone ready? Here we go. And you see, we completely vaporized the aluminum foil. We changed all of that 3,000 joules of electrical energy into heat and into light and into sound. And so there's a lot of energy in electricity, as there is in many other things. Now, we can store energy not only in electricity, but we can also store energy in magnets, because magnetism is another form of energy. Now, one way to make a very powerful magnet is with a coil of wire through which we pass an electric current. And we have exactly that right here. This red wire goes around this iron core several hundred times. And I'm going to connect the wire here to an ordinary car battery that makes about 12 volts. When I disconnect it, all of the energy that's stored in the magnetic field, about 50 joules worth, is going to discharge into a little strip of aluminum foil right up there. So are you ready? First, I store the energy in the magnetic field by connecting it to the battery. Then I disconnect. So watch yourself. And you see, again, it completely vaporized the aluminum foil. Now I'm going to repeat this, as someone asked me to do a moment ago, except this time there's no aluminum foil there. So I'm going to store the energy in the magnetic field, and then I'm going to disconnect it. Now remember, energy can't just disappear. It always has to be converted into something. So we don't have a foil to explode, so let's see where the energy will go. First we store the energy, then we release it. Can you see the big spark that forms right here? So all of that energy goes into making a plasma, an ionized gas that's very hot and very intense. And so that's one way we can convert energy into a form that's other than the way it started. So that's magnetic energy. Now another example of magnetic energy uses this gadget right over here. In this gadget we have about a coil with several hundred turns of wire, and that wire is connected to a plug that I'll plug in the wall back here, a wall socket just like you have at home. And when I push the button here, that will energize the magnet and it will magnetize this piece of iron. Before I do that, however, I want to put over the iron a little aluminum ring. Now when I push the button, the electrical energy will change into magnetic energy. The magnetic energy will induce an electric current in the aluminum ring, and we'll see what happens. It causes it to jump up. So the magnetic energy has gone into kinetic energy of motion, and the kinetic energy then is converted into potential energy as the ring rises up. Now we can do this a little bit differently by adding an iron bar. And the iron concentrates the magnetic field and makes it go up higher. So we will now have more magnetic energy, and so we might expect the ring to go up a little higher. Once more. So it goes up pretty high. Now, you may wonder if there's a way to make it go even higher. And in fact, there is, because this ring moves because an electric current flows in it. And one way to make more electric current is to make this a better electrical conductor. And it turns out there's a way to do that. If I put it in this little dish, and if I cool it with the liquid nitrogen, it will become a better conductor of electricity. Now, this also gives you a good opportunity to observe the liquid nitrogen. It looks like a dish of boiling water. But it's not boiling because it's so hot. It's actually very, very cold, but it's nonetheless plenty hot enough to boil the liquid nitrogen. Now, of course, as we wait for a while, the glass cools down, and the aluminum ring also cools down. And when they cool down to the temperature of the liquid, then the boiling will stop. And then we know that the ring is at the same temperature as the liquid nitrogen, 321 degrees below 0 Fahrenheit. And that's very, very cold. And when something is that cold, when aluminum is that cold, it is about a 7 times better conductor of electricity than it is at the temperature of the room. So now you see the boiling has just about stopped, and so we know it is nice and cold, and it is a good electrical conductor. So I can now put it over the aluminum core, or over the iron core, and I can energize it again, and you see it goes up pretty high. Would you like to see that once again? Do what? Put. Okay, I'll try anything once. I'm not responsible if it goes through the roof. Okay, well, these are examples of magnetic energy. I want to now talk a little bit about the energy of light. Now, you know light has energy, and I've even shown you examples over here of converting electricity into light energy. But you may not know that you can go the other way. You can convert light energy into electrical energy. And here's a gadget that does that. This is something that we call a solar cell. It's a little panel that absorbs the light, and it makes an electric voltage on these 2 wires right here. And so we're changing the light energy into electric energy. The electric energy then goes into this motor where it makes magnetic energy. The magnetic energy, in turn, is converted into the energy of rotation of this little wheel on the front. Now, it's not quite enough light in here to make it turn around yet, and so I'm going to shine this bright light on it. And you will see it go around. And so this is light energy to electrical energy, to magnetic energy, to motion energy. And so this would be very nice, and you would say, well, we maybe could run all of our cars and the motors in our refrigerators and everything that way. And that would be true, except it takes a pretty bright light, and the motor is not a very strong motor. In fact, if you go outside on a day when there's no clouds and the sun is almost directly overhead, like at noon, the sunlight that we get is a little over 1,000 watts on every square meter of the ground. So if you imagine a little plot that is this size by that size, we get about 1,000 watts of energy from the sun in that much area. Now remember, that's when the sun is directly overhead, when there are no clouds in the sky. Of course, a lot of the time, it's a lot worse than that. It's cloudy or it's night, and so maybe on the average, we would only get about 100 watts. Not only that, but solar cells are not very efficient. They convert light into electricity only with about 10% efficiency. That means we would only get maybe about 10 watts out. And that's not very much, because remember, to light a light bulb like that, we need 100 watts. And so, although solar energy has lots of very attractive advantages, it's clean and it's free and so forth, there's also not all that much of it unless we're willing to cover a large portion of the Earth with these kinds of solar cells. And solar cells are still moderately expensive. So it's a little bit expensive in terms of the solar cells, but cheap in terms of the fuel, because it all comes from the sun, which, by the way, is ultimately where essentially all of our energy comes from. For example, and my assistant Kevin pulled me up there and gave me 3,000 joules of potential energy, you might ask, where did that energy come from? It came from his muscles. Where did his muscles get their energy? It came from the food he ate this morning. You know that when you eat a certain number of calories, you're actually giving yourself energy. And in fact, a food calorie is about 4,000 joules. Another way to say it is, if you eat something that's about 250 calories, let's say, like a big jelly donut, that's about 1 megajoule of energy. Remember, the power company charges you about 2 cents for a megajoule of electricity, or about half a cent for a megajoule of gas? How much does a jelly donut cost? So food is actually a fairly expensive form of energy, but we all eat lots of joules worth of energy every day, and it's important. And that energy, of course, ultimately came from the sun, because the food that Kevin ate grew because of the sunlight that shined on it. And so the sun is ultimately the source of all of our energy. Well, the last thing I would like to mention to you, the one last form of energy, is what we call nuclear energy. And nuclear energy is a very important form of energy, because ultimately the energy that we call nuclear comes from mass itself. Here I have what we call a 1 kilogram mass. It weighs a little over 2 pounds. And yet, if we were to convert all of this mass into energy, the amount of energy we would get out is about 100 million billion joules. Now, people often say that you can convert mass into energy, and a lot of people even know the equation, E equals mc squared. But in fact, it's more accurate to say mass is just another form of energy, like all the other forms that we've been talking about. And so in a nuclear reactor, we can actually convert the mass energy into energy of heat and ultimately into electricity and other useful forms. In a nuclear reactor, we convert about 0.1% of the mass energy into other forms of energy. So there's a lot of waste involved with nuclear fuel, but nonetheless, it is a tremendous amount of energy we get out of a very small amount of fuel. Now, one form of nuclear energy that you've probably heard of is called nuclear fission. And I have a good example of a nuclear fission reactor down here, but I will need a volunteer. Would someone help me? Someone from over here. All right, come down here. Stand right here and turn around, face the audience. Tell us your name.
Riaz.
Riaz?
Yes.
Riaz, okay. Have you ever seen a nuclear power plant?
Only on TV.
Only on TV. You know, nuclear power plants have operators, and they sit there at the controls, and they have to push all the buttons right. You know what happens if they don't?
Go boom.
Well, a nuclear power plant can't explode, but it can do bad things. It can release radioactivity, and that's one of the reasons, that's one of the reasons we have to be careful with nuclear energy, because there's a lot of energy involved in the nucleus of certain atoms. What we'd like you to do, Riaz, is turn around and walk right around here and stand with your back against the wall right there. Face the audience. That's fine. And put this in one hand, but don't pull it yet. Because what we've given him is a string. The string is attached to a little trap door on the top of a container that has in it a whole bunch of ping pong balls. Each ping pong ball is sitting on top of a mouse trap that's set and ready to go off. And above that trap door are 3 ping pong balls. And this will illustrate the principle of a nuclear fission chain reactor. Are you ready? Pull very gently but firmly. Keep pulling. A little more. A little more. Thank you. Of course, a nuclear reactor is a little more complicated than that. But the idea is the same. In a nuclear reactor, we use neutrons instead of ping pong balls, but the idea of a chain reactor is the same. Now, the final thought I want to leave you with is that there is yet another form of nuclear energy that scientists have been working on for some 40 or even 50 years. And it's a form of nuclear energy that we call nuclear fusion. And no one has made a nuclear fusion reactor on the Earth yet, but people are working on it, and someday it will happen. And we know that it can be done because all of the stars are nuclear fusion reactors. and they burn very efficiently, and they produce lots and lots of energy. And so if we are able to do this in the laboratory, that will be a wonderful achievement that will give us vast amounts of very cheap and clean energy. So stay tuned and watch carefully to the progress of making energy by this new method of nuclear fusion. Well, this brings us to the end, and there's one last demonstration I would like to do for you. It's always traditional to end these shows by making for you a cloud. And we do that using a container that is filled with liquid nitrogen, a very large amount of liquid nitrogen, and we force nitrogen gas into this container. The liquid then comes out through these holes on the top. It will come up and heat and cool the air. When the air is sufficiently cold, the moisture in the air will condense. The water vapor will condense into tiny droplets of liquid water. And that's what we call a cloud. And with that, I thank you all for coming.
Thank you.